You'll recall that in molecular orbital theory, the electrons in a molecule, or in the case of silicon here, a large covalent crystal, are not shared just on individual atoms, but are shared around the entire molecule, or here, the entire covalent crystal. Silicon's electrons here are distributed throughout this valence band. But silicon is a semiconductor. Electrons, if they hop up into the conducting band, can move around the covalent crystal, for example, away from this negative electrode. Now, silicon is a semiconductor. It is able to conduct electricity somewhat, given that its band gap is not excessively large. Other elements like copper would have much, much smaller band gaps, and electrons would be able to hop up into the slightly higher energy much more easily. Now for silicon, though, to conduct, its electrons need to overcome this moderately large band gap, which occurs most easily if the silicon is energetic, if the silicon is hot. We can see here that silicon is a poor semiconductor of electricity, but it can conduct better if it's heated. The electrons can hop up into the conducting band and move easily throughout, whereas they're stuck in place in the valence band. But another way to make silicon a better semiconductor is to dope it. That is, to add in or replace silicon with other elements like boron here or phosphorus. If you dope silicon with boron, an element in group 3 which has only 3 valence electrons, and unlike silicon's 4, there will be this absence of an electron in this position, and hence a positive area. Now, whereas silicon, its electrons were stuck in place previously, having this doped conductor, we now have this positive area, a hole, where electrons now can move in. So in the presence of this negative electrode now, electrons in this solid would be repelled by that negative electrode and attracted to the positive electrode over here. Electrons would be able to move fairly easily because there is this hole, this blank space. You see down here that when this electron moves over to the left, the hole actually moves to the right. You can also conduct with other elements that have more than silicon's 4 valence electrons. Conduct with group 5 elements, like phosphorus. It has 5 valence electrons, not 4. Having one extra electron, there's now an extra electron already up in the conducting band. Having this electron already up in the conducting band, there are no other electrons blocking its transport, and so this negative electrode can repel this electron up in the conducting band, and the electron can easily move. So you see that it hops over, and so it's moved to the left. So over here we call this this electron a free electron, whereas we call this absence of an electron a hole. Now you can get holes and free electrons by doping p-type semiconductors, that is positive types, that is the semiconductors with holes. You can get those by doping with elements that have one less valence electron than the semiconductor. So in most cases, that's going to be group 3 elements. You can get n-type semiconductors, which are negative type, that is, they have free electrons, by doping with elements which have one more valence electron than the semiconductor. So most typically, if you're dealing with silicon, that means that you're going to dope with some group 5 element. So some examples of some group 3 elements that you might dope with are boron, Or also you could dope with other things like gallium or indium. And to get an N-type semiconductor, you would dope with phosphorus or arsenic and possibly even antimony. Thanks for watching, guys.